Bill here. This is the hash.cpp source file in my simple chess engine project. Okay, let's have a look. So this is all to do with the hash or the transposition table. So we include our globals. Now what we do is we have, for every piece on every square of the board, we have a table for white, which is this. We have one for black, and we have two hash tables. The second one I've called lock. They could be called hash 1 and hash 2. The reason for this is because there is a very high chance of different positions having the same hash key. So the idea is every position can be used to generate a pseudo-random number, which is its hash key, and you'll get clashes where the program will think two positions are the same, where in fact they're quite different. So what you do is you have a completely different table called the lock, which is the second hash table, so that gives a completely different score for a position. So the odds of two different positions having the same key and the same lock, which is really a second key, are very, very low, sort of like 1 in a trillion, whatever. So that's a clever idea which stops you getting clashes in your hash table. Okay, so what happens is you've got a similar sort of deal with the pawn hash table. The pawn hash table is much smaller, uses what because we're only storing pawns. So basically each position can be 1s and 0s to represent white pawns, another one for the black pawns, and that can be converted to a random number. Okay, so we're setting up maximum sizes for the pawn hash table. So we've got a variable called current key and current lock, so that gets changes every time a position is updated. So pawn hash table has the lock, so that's a second key, and a score. So what it means is we look up the position. If we have the same key and the same lock, we return the score for both sides, which is the score of the pawn structure. Then we create an array of hash pawns. Okay, so that's an array of the above structure. So that stores information from all the pawn positions we look at and their scores. That's all gets stored in the pawn hash table. And then we've got the current key, current lock. Clashes and collisions is mainly for debugging. It sets the maximum sizes of the tables. And we have, whoa, that should be around the other way. Okay, so we've got the entry in our main hash table. So we have the lock, we have the move, and we have a number, which is we'll see what that's used for later on. Okay, so what is next is, oops, that's around the right way, and this one's around the wrong way. Okay, so randomized hash is called when the engine started, and we populate all these hash tables with random numbers, so that generates random numbers up to the size of the position. Okay, then we have some. We use pointers to make the hash tables, so that means they can be of different sizes depending on how much memory is available. Okay, so random generates a random number. This is not the best way to generate random numbers, but it'll do for a simple engine. And then when we create a pointer with 3, we need to, a pointer with new, we need to free it up with delete. So that's what this does. So that's what this does. Then we have this frees all the hash tables, so it just sets us back to the first position in the hash table. Okay, add hash, adds an entry to the hash table. So we pass to it this S, which is the side to move, the move, and a value for number, N. So we get a pointer. We make a pointer to the current entry in the hash table based on the current key, so it's a lookup table based on the current key. Then we store the lock, the move and end. So that's how we add an entry to the hash table. Okay, so we update the key. So key represents a position. So add the key. So we look at the side to move, the piece, and the square. So we XOR the current key with the values from the hash table. We do the same. If it's black, we use the black ones. If it's white, we use the white ones. Okay, so get lock gets the current lock from a position. So what we do is we do the entire board. If the square is not empty, depending on the colour, we're going to adjust the value of lock based on the scores in the lock tables. Okay, so get key, so it's a similar sort of thing. We loop through the position if the square is not empty, and we adjust the key according to the values in the table. Okay, so lookup returns the current position. It will return true or false. So firstly, the lock's got to match the current lock. If it doesn't, we return false. Otherwise, we can fetch the move that gets stored in the hash start and hash test, and we return true. We have get pawn key, does something similar. We work through the board and we work out a value of the key for the entire position. Get pawn lock is similar. Add pawn key updates the current pawn key and lock. Add pawn hash. Adds the lock and the pawn score to the pawn hash table. Okay, it's pretty straightforward. Look up pawn. Determines whether the current pawn position is in the pawn hash table. So we look it up. If the lock and the matches, if the locks match, it's true. Otherwise, it's 0. Okay, just want to return the hash score, the pawn hash score for white. Return the pawn hash score for black. And I think that might be it. So it's quite a lot to the hash table, so they need to be created. They need to be populated at the start with random numbers. They need to be updated every time the position changes. You need to look them up and they can return scores and so on. So the hash table is very good because it means you can sort the moves much better, which saves a lot of time. You have to you can search much fewer positions, and with the pawn hash table it saves you having to keep calling the evaluate pawn function, which is pretty slow. So it speeds your program up in 2 different ways. So that's a brief look at the hash tables. Thank you for watching.